So next type is type 4, bars with varying cross section. As you can see from the figure, first one, it's a uniformly taper circular bar. So uniformly taper means reducing in diameter. So the bigger diameter is D1, the smaller diameter of the taper is D2, length of the taper is L. So we have a formula for this to find elongation of such bars. So elongation of such bars is total elongation equals to delta L equals to F into L. F is the force being pulled, L is the length of the taper, upon pi by 4 into D1, that is bigger diameter, into D2 smaller diameter, into the Young's modulus of the bar. So this is for the uniformly tapered circular bar. Now for uniformly rectangular bar. So as you can see from the figure, second one, it's uniformly rectangular in cross section and it's a taper bar. So the dimensions are: bigger side is called as A, smaller side is called as B, and L is the length of the taper, and T is the thickness, small t. So we have formula for this elongation. So formula for this is delta L equals to F, that is force being pulled, L is the length of the taper, upon T, that is thickness of the taper on a rectangular bar, E is Young's modulus, into A, bigger side minus B, into log of ln of A by B. So taking a small example, first one, a steel plate. It's a plate means it's a rectangular cross section, has uniform thickness 20 mm under the axial load of 80 kN. Its section tends to be found is 0.17 mm. Find the Young's modulus of the material and maximum stress in the bar. So the expression is already known, that is 0.17. So using the equation delta L equals to PL upon TE A minus B log of LB by B. So the delta L is 0.17 is equals to, load is 80 kilonewton, so 80 times to 3 newtons. L length of the taper is 500 upon thickness of the taper rectangular bar is 20. E, which is unknown, and A is the bigger side, that's 80. B minus B is the smaller side of the taper, that is 40, into log of 80 by 40. So substituting the answers, we can simplifying the answers, we can get the Young's modulus E as 2.03867 10 to 5 Newton per mm square. So maximum stress in the bar will be load by least area of cross section. So when your least area of cross section means the smaller end, that is at the 40 into thickness 20. So here the maximum stress will occur at the least smaller side of the taper, that is load is 80,000 upon least, that is 40 side into thickness 20. We get the cross section as 40 and 20. So the answer is 100 Newton per mm square. So we'll take a second example. So find the total elongation and maximum stress in the material as shown in the figure under the axial load of 20 kilonewton. E is 200 giganewton per meter square, nothing but giga pascal. Newton per meter square is pascal, so it's gigapascal. So first find the elongation of section 1. So we'll take the left section as section 1. PL1 A1E. So P is 20,000 common, into L1 is 400 for the first section, 25 diameter, into A1 is pi by 4 25 square, 25 diameter section, into E is 2 10 to 5, which is already given. Next find the middle section, that is find the elongation of middle section, that is taper section, that is delta L2 is P into L2 pi by 4. Since it's a circular section, so pi by 4 D1 D2 into E. So P is 20,000 into L2 is 400 here, upon pi by 4 D1, that is the bigger side is 25, and D2 smaller side is 15, as you can see from the figure. So 15 25 into E 205. Substituting, we can get the answer for delta 2. Similarly, calculate for delta L3, that is the last section, small section. So PL3 pi by 4 D3 into E. So pi by 20,000 into 400 upon pi by 15 square into 20 raised to 5 E equals to, we should calculate the answer for this. Now lastly, to find total elongation, we can delta L is delta L1, delta L2, delta L3. We can just add the three elongations of three sections, so you can get the answer for total elongation. So maximum stress in the material tau max is pi by 4, the smaller section, that is D3, that is 113.2 mega Pascal Newton per mm square. So we'll take one more example. A plate of 60 mm thickness tapers uniformly at 80 mm to one end, to 50 mm to other end, to length of 800 mm. If the plate is subject to a load of 200 kN, find the extension of the plate. E is 2 × 5. Also calculate percentage area. Average area is used for calculating the extension. So total extension bar, you can use for, it's a rectangle plate. So you can use the formula delta L is P into LB, LP F into L, T E A minus B, L of B A by B. Substituting the answers for P 120 3, L, that is 800 upon T 16 thickness, E, that is 2 × 5 given. Bigger side is for 80 minus smaller side is 50, ln of 80 by 50. So you get the elongation as 0.747 mm. Now if you use the average area, so average area means area at the bigger side is 80 into 16, average smaller area is A1 is 15 into 16. So average area is A2 plus A1 by A2, so 1040 mm square. The total extension area is used. So PL by A. So if we use a normal formula, conventional formula, PL by A, using the area average area, so we get 0.46154. So to find the percentage, so bigger minus smaller whole upon bigger into 100, we get it as 0.47, 0.46, 0.47 is 100, we get 1.8% of error. So this was about the type 4 of bars with varying cross sections.